So I'm Célian Bamba, and I'm a postdoc in the Caroline Harris lab. And I'm going to talk about chronic neuropixels recording with a focus on reusable chronic neuropixels implants. And so this is the outline of my talk. I'm first going to introduce a few reasons why you may want to use chronic implants. Then I'm going to talk about the general principles of how it works and get to more details of the implantation and explantation procedures. And finally, I'm going to show some results of what you can obtain with those. It's been hinted at by Nick also just before. And finally, I will try to highlight a few of the challenges that, in my opinion, still remain. Okay. So why would you want to do chronic recordings? I think historically, the main reason why people have wanted to have the probes with which they recorded neural activity attached to the skull was to be able to do freely moving recordings. So this is an example with the NeuroPixels 1.0 from the Church lab in 2019, where the mouse here is being implanted with a recoverable implant that I'm going to describe a bit later with the NeuroPixels 1.0, and it's freely able to move around, and so they're able to recover from the brain at the same time. So that's one reason. Another reason is to track neurons across days, or I'm saying neurons, but it can also be at least a brain region, the activity in the brain region. We'll see in the next talk that this can be pretty tricky. And I'm not going to go over this because Anna is going to go into more details, but basically she used natural image responses to see whether the neurons in primary visual cortex that were tracked were actually the same over days, and this was for over a year time. So a third reason, which I think Nick just mentioned, is actually that if you record chronically and you have a whole brain approach, which means that you're interested in what happens across the whole brain, you minimize your setup time. What do I mean by that? Is imagine now you have your NeuroPixels 2.0 with 4 shank that's been inserted in the brain. So you have each of the shank here and the brain is at the back. You cannot record from all the channels at the same time. There are like about 5,000 channels total, but you can only record from 384. So that would correspond to just one little bank here, okay? And so if you're interested in recording from the whole probe or the whole section of the brain that you're covering here, doing acute recording, you will need to insert the probe on day 1, record from that little bit, then take the probes out and do the same thing on day 2, and so on and so forth. And each day is going to be, about an hour setting up and then removing the probe at the end. So that takes quite some time. Whereas with chronic recordings, you can just, plug in the mouse in 2 minutes, and then you record this section on day 1, and this section on day 2, and so forth. So then you can cover the whole probe. And in that case, we had over like 800 neurons going from frontal cortex to deeper regions of the brain. And I'm just going to highlight 2 other reasons why you may be interested in doing chronic recordings. The first one is if you're interested in recording brain activity across contexts. And I'm not only talking about, freely moving contexts, but also even head fixed if you're interested in a certain type of task on one hand and another type of task on the other hand, and you want to compare the brain activity in these 2 tasks. This is something that's very easy to do in the set with chronic recordings, and you can record the same neurons across the context. And also, this is something, the last point is something we do quite often in the lab. Actually, we can share mice across experimenters. 3 or sometimes 4 experimenters can use the same mouse if they're interested in the same regions of the brain. And this is pretty easy to set up. This is actually how I started my postdoc, was using Anna's mice that were implanted. So there are 2 main general principles. The first one is a permanent implant where you cement the probe to the skull. And the second one is, this is an expanding field, but this is reusable implants where you can reuse the probes across mice. Okay, so I'm gonna now detail a bit more these 2 principles. I'm gonna go over the permanent implantation very quickly because my main expertise is on reusable ones. But basically, the idea is that you insert the probe into the brain. So this is supposed to be a probe with here the shank going inside the brain. Let's say you're interested in recording from that region in green here, and then you would actually just cement it to the skull and cover it with a protector so that when the mouse bumps into things in its cage, it doesn't damage the probe and so on. And so with that, you can record across many days, with using a single probe. The issue is that at the end, it's very hard to explant these probes. I think some people do it, they drill it out. I don't even know how they reuse it, but basically this is something where usually you just lose the probe in the brain. And as you may know, these probes are quite expensive, and this is not something that every lab can afford. So another type of implant is reusable implants, and they come in different flavors, but usually you have a general principle, which is you have the probe still, and you have two types of module. One thing that I'm going to call the payload module, which is actually the one on which you're going to attach the probe and you're going to reuse. And then the docking module, which is the one that's going to be attached to the skull. And how does it go? You build these things before the implantation. So first you attach the probe to the payload module, and then you're going to assemble these two pieces, these two modules together to form the whole implant. And in the end, you can go ahead and insert that whole thing into the brain, and then cement only the docking module to the skull. Okay, so this is how you perform the basic implantation. And then at the end, the main advantage of these reusable implants is that you can, once you're done, you can come with an external holder, attach it to the payload holder, then detach these two pieces that are usually held together by screws. And then you can retract the payload module, recover the probe, and reuse it again in another animal, or the same animal if you're interested in that. Okay, so that's the basic principles. So as I was saying, these reusable implants, they come in a lot of different flavors. I've listed here all the ones that I know of and that have been described more or less somewhere. The first one is this one that's been developed by the Churchill Lab, and this is actually using, I think, at least in this paper, it was Neuropixels 1.0. And you can see that here you have the probe that's sitting here and it's attached to this casing here. And only the casing is actually cemented to the skull. So then you can just drill that out and then recover the probe that is only momentarily attached to the casing. And in that case, you also have this bigger holder here, which holds the head stage for freely moving. So that's one. Another one was developed by the Brody Lab. And here, I think they used it mainly in rats. So you have this external chassis that kind of ensheath the probe, of which you can see the shank here. And what's cool with this one is that you can have several of them together, up to 4 implanted in the same animal. Another one which has been has 2 designs, one for 1.0 and one for 2.0 probes, and I really like this one with it's very well engineered and nicely detailed. So you have here the payload module, and actually at the front here you can see a case in which the head stage is being fixed, and it's attached through these screws to the docking module, which you can see here, and the shank is sticking out of it. Okay. This one I know a bit less of it, but it's mainly used in rats. And actually you can see, so the probe is here, then that thing would slide down and would cover the probe actually. And it contains the head stage, but what I wanted to emphasize here is that this big thing, so it's pretty heavy, but it's mainly used in rat, and this is used to cover and protect the whole probe as a whole. Okay. And then there are a few others that have been developed more recently. This one is from our lab, and the idea behind this one was very inspired from this design, which is really good. And the idea was to push it towards being more lightweight, more flexible, and a bit less expensive. And so on this one, and just like this one, you can use 2 probes on the same implant, and you can see here the payload module and the docking module. I'm going to get back to that. And then there are also some others, and I'm going to emphasize some of their qualities next. So one thing that I think is pretty important when you start doing chronic recordings is to ask specific questions. So I've tried to list a few of them here, because this is going to determine which of the implants you use. So there are lots of implants. I mean, I've listed, I think, something like 7. And I think they all have different properties and features, and they kind of complement each other quite nicely. So the first question you may want to ask yourself before you start is which brain area you're interested in. And this is important for different reasons. The first one is some implants have been tested only in some areas, although I think they would generalize quite well to different areas. But the most important one is what's the angle you will need to actually reach that region. And depending on the bulkiness of the implant and other features, you may want to choose depending on that. Depending on which animal you're interested in, you may want to check what's the weight of the implant, because some animals are actually some implants are pretty heavy, on the heavy side, and some others have been specifically designed to be lightweight. And I know, for example, for mice that, mice is about 20 grams. Male mouse is a bit heavier, but we very often use both male and female mice, and that are also water restricted. So that's about 18 to 20 grams. And so we need to bring this weight, this overall weight, below 2.5 grams at least. Then for how long you want to record, if you're interested in super long experiments where you want absolutely the most stable experiments, then cementing the probe may be the way to go. Otherwise, if you're recording for a few days or weeks or months, a reusable implant can be good. And then finally, the level of flexibility that you may need. How many probes do you want to get in? Do you need these probes to be independent of each other, and so on and so forth? So I've tried to put here, I've been updating this table that's been used over the past few courses. So each column is a different implant, so the ones I know of at least, and each row are the different things you may be interested in, so in which organisms it's been used, so mostly mouse, rats. I know our implants currently tested in marmosets and also possibly in ferrets soon, but this is mainly mouse and rats. Also which brain area they've been tested in, which NeuroPixel version, how many probes you can implant. So some of them can only do one probe, and other types of implant can do up to 2 or up to 4, either in a fixed manner, like this one and this one, or in a more flexible manner, like this one. The weight, finally, this is very hard actually to find the actual data for the weights, because when it's reported, it's usually either only the parts or using the weights, adding the weights of the probes also, or there's a whole sorts of combinations using the cement, adding the cement and so on. So I've put some indications here, but they're not perfect. And finally, some specific features here. Okay, so some of them, like this one, are super robust. This is the big one that's a bit bulky, but this one is super robust. It's also pretty heavy. Some others are very lightweight and low cost, like these two. And some others are you can customize the position and depth and angles of each probe independently. Finally, most of them have been already released and are publicly available, either through actual papers, peer-reviewed papers, bioRxiv, or on this nice protocol.io webpage, which is very detailed. I really like this implant because it's very detailed, the whole procedure. And some others, I think, from Yoizuga, can be available upon request. Okay, so now I'm going to get into a bit more details of how we actually perform the procedure and how am I doing with time. I think I'm on time. I'm going to focus on only the implant that we've been designing here in the lab, because this is the one I know I know best. And so apologies for all the other implants, but I think most of them have pretty detailed procedures, and some of the principles are actually shared across all different implants. Okay, so this is the implant. This is in the exploded version. You have here the payload module on which you can affix two probes, okay, in that case, two 4-shank 2.0 probes, one on each side. The flex is coming here. And then you can cover these probes with a lid on each side also. You can see here the inside slot is to actually insert the folded flex here like this. I can show you a picture later. And then the outside little loop here is to, as you can see on this side, to tuck in the flex to make it as compact as possible. And this would be the overall thing that you reuse across mice or across experiments. And then you assemble it with this docking module, which has this funny shape here. For different reasons. This is to put in some screws that are going to be connected here to attach the two. And these little merlons here are to actually increase the surface available for cementing it. And this is the assembled version for the dual. So you have two probes, NeuroPixels 2.0, and we also have a version of the 1.0 that's been tested in different labs. All right, so I'm going to start with the probe preparation, which is actually quite a crucial part that can be a scary one. But I think from what I've heard and my own experience, this is not usually where probe breakage happens. So you usually start by affixing the one probe to the payload module, which you can see here. So you would just come, usually I do it manually, put a little bit of epoxy at the bottom of the payload module, and then assemble the two by hand. So this is what it looks like. Blue tack is very useful in that process. You can then align the shank to the the same axis as the payload module using graph paper. This is one technique used by Giovanna Catarino and Jose Teixeira in the main lab, which I found really useful. And then you can assemble the lead. So this is a 1.0 actually. This is 2.0, sorry about that. But then you would fold the flex inside the little loop inside. This is just because it's easier than to manipulate. Then put some dots of glue on the side and then just close it. And this is a good time now, once you've assembled it like this or with the lead already, to sharpen your probe so you can have a specific holder that we provide as a CAD file that you can print. Yeah, I forgot to say that, but all of these can be 3D printed either by outsourced company or in your own lab if you have resin printing. And so yeah, you just hold that thing and then you come and sharpen it. It's been mentioned in the previous talks, but usually sharpening the 4-shank probe is pretty easy. It's just as easy as a 1-shank probe. Just have to be careful that they're all at the same level. Then you can add another probe to the other side. So this is what you end up with. So this is just the payload holder that I just talked about, which you can use to sharpen your probes. Here you have the payload module with the leads on each side, and then the 2 4-shanks coming here on each side of the payload. And then the flex is here because then you can just plug in the head stage here and record. All right, and this is usually, so the second probe, you sharpen it beforehand and we have a specific holder to do that. So then you can just add the ground and reference wire. In this case, what we do usually is to connect everything together. And then the final part is to assemble the payload. So that part you can see on the top with the docking module. And for that, we use this specific contraption where you have a payload holder, which looks just like this, except it has this space. We have a docking holder, which looks like this thing with 3 arms, and in which you can fit the docking module. And then we have this constructor, which has these long arms on which the docking holder will slide. And this looks just like this when you've assembled everything. So this is your probe, and you want to assemble this part with this part that is fitting into this holder. And so because everything's been designed to be well aligned, you can just slide it in and then add the screws to these little pieces here on the side, connect everything, then release that part with that screw, take it out, and then you're ready to go and you have the final assembled implant. And just before you start, you may want to fill in any gap with quick cast. This can happen if the thing is not properly mounted. This happened to us, especially at the beginning, when we were kind of fiddling a bit with the design. But for example, here you can add a bit of quick cast to avoid any kind of dust coming in. And finally, just before you experiment, you want to paint the probe with dye. So usually we just have a Eppendorf of dye, and we just dip that thing in. Okay, so what does the setup look like? Basically, it looks just like this. I've only put the bare necessities here. You have a manipulator, so micrometer precision manipulator here, which is holding the rod. And here you have the probe that's at the very tip of that thing here. And you're going to use that manipulator to drive the probe inside the brain of the mouse that's going to be head fixed in that setup here. So this is the kind of head fixation setup we use. In addition to all of that, you're going to have an anesthesia setup. I like to do this under anesthesia because, it's much better for the mouse and it's also easier. So you would have in front of the mouse, you would have the gas mask, and here you would have also a heating pad. So this is just the controllers for the manipulators. And one thing that I really like is to use a microscope that's very flexible to see everything around. Okay, now I'm going to go quite quickly through the implantation process. It's quite simple and it's very similar to what you do in acute recordings. So basically, you start by doing a craniotomy. In that case, we're going to do bilateral craniotomy over frontal cortex. You have to make it small, keep the brain wet, otherwise things just harden and it gets harder to get in. And then you can either use a drill or a biopsy punch. We find the biopsy punch to be quite useful to have a clean craniotomy. Then you put some Duragel. You can let it sit for about 10 minutes. And then you just come with this probe holder and you just drive the shanks down into the brain. So this is schematics. This is what it looks like in real. So you can see here 2 craniotomies. This is a dual 4-shank insertion. And you can see that on each craniotomy, you have some blood vessels. So it's a bit of a game to find a place where you will both hit your targets, obviously, once you're in the brain, but also avoid blood vessels. Okay, so you can sometimes go through some of your blood vessels when they're very small, but I would advise against that. But for the big ones, I would definitely avoid that. And you can use also the microscope that I just mentioned that's very flexible to watch for the probes bending as you're going down. And in the end, you try to go down quite slowly. Just to mention, this looks totally enormous compared to the size of the brain, but that's because the mouse brain is pretty small. And this is actually the minimum height of the NeuroPixels probe, right? So we tried to make it as small as possible overall. Then what we like to do is to add UV cement that's pretty thick and malleable, and you can then shed light as soon as you want to make it harden, so it doesn't flow in and hit your probe. So you just connect basically the docking module to the bone. And now is a good time to connect your ground to the skull screw if you're interested in that. We've tried both, and actually sometimes you get really good signals even without it. And finally, we just cover the whole thing with dental cement that's very fluid and going into all the different, little merlins that we have here and so on. So now it's very stable and sturdy. Finally, you can just, unscrew the holder that's up here and lift it, and then you have your mouse that's ready to go. So this is just a short example for such a recording, but now in rats. And because that thing, so this is a 1.0 implant. You can see it's a bit taller. It's only on one side here. It's a single implant, and the ground is going down there. And basically here, this is work done by Sugupta from the Viken Iser lab. And what they did was to actually cover the whole thing with this specific, I think it's coming from Spackjack Gadgets, kind of wall around it to protect it. And then as you build it up, it covers the whole thing and serves also as a Faraday cage. And finally, you can, on top of that, you can use this device on which you can record the brain. Actually, I think it saves everything on an SD card, so you can do wireless thing. Okay, so now the explantation. This is very quick. So you have your mouse, you head fix it back in where you usually in the same place as you inserted and implanted. You detach the ground if you have one. Then you come over and attach the payload holder to the payload module. And now it's time to really carefully align it, because any kind of friction or misdirection will make it very hard to remove. You can then unscrew the payload from the docking module and finally just lift it up. And that part can be pretty difficult for different reasons. So you may want to recheck the alignment, remove any kind of quick cast that's in between, check for dust. And actually, I just realized now that the shanks are still in there. So this is not supposed to happen. And I don't think it's ever happened to me. This is just a glitch in my schematics. Hopefully it won't happen to you either. And yeah, and now you can reuse that the probes that you've just retracted. Sometimes it can happen that the probes are pretty dirty. You can see it here, where after extraction, you see some kind of dust on the shanks, and these can be different things. It can be some things coming from the cage of the animal and going through some holes in the implant. So now we've tried to fix it actually over the years, and we use this quick cast also to cover the last holes. Can also be the Duragel that's sticking. Anyway, different things can stick, so you may want to give it a bath of tergazyme, usually overnight, then deionized water, and when it doesn't come out, we have tried to use stronger solvents like Dowsing, and this happened to actually work quite well. Okay, so now I'm gonna go over a few results of what you can obtain. This will be, okay, so this is actually dual 4-shank chronic recordings that we've done, where the first probe was inserted into frontal cortex here and then striatum. And the second probe, which was more at the back, was in the somatosensory cortex and then in some deeper regions here, including striatum. And what I'm plotting here is actually the raw signal in this little chunk. So there are a few, each line here is one channel. And I'm recording from this little chunk here. You can see both that the noise level is pretty low. You can clearly see some spikes. This is on day 16. And as time passes, we get to day 88, and you can still see some spikes, and the signal, the noise is not increasing so much on that same implant. And this is kind of the same for the second probe. What I'm plotting here now is actually counting the number of spikes on each channel. Okay, so this would be the color map is the number of spikes on each channel, and the depth along the probe, so this is spanning the whole length of the probe, so this whole thing is actually along the y-axis. And the x-axis is actually the number of days that we've been recording from that mouse. And this is for shank 1, 2, 3, 4. So these guys that you see here actually have been recorded at that time. And so you can see the same thing for the two probes. And you can see different things. The first one is that overall it remains quite stable. You can follow these spikes here throughout the whole time for more than 100 days. You can also see that sometimes there's a bit of unit loss, as you can observe here. But this happens, it's actually increasing and then decreasing, as you'll see in the next slide. And so that's one thing. And the second thing is that actually, you may not have noticed, but on one occasion, you can actually record only one bank. So this is one recording, all this area here. I mean, actually, this is over many days, but this is one recording. And here to combine all of these things, it took me something like 8 different recordings. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and this is double along the probe. So this is what I'm talking about when I was saying that to record this whole thing with minimal setup time, actually the chronic recordings, it may be one way to go. So now this was just counting the number of spikes. We see that it's quite stable, but one metric that's commonly used is the number of neurons across days that's been recorded across the whole probe. And as a comparison, I'm just showing here probes that were in visual cortex. This is work by Anna Lebedeva. And so this is the number of days this implantation. And this is the neuron count. Watch out, because this is a log scale. And the reason why is because we expect the decay to be linear in a log scale here. But basically, so you have 3 probes, and these probes were cemented in the brain. So this is the most stable we can expect. And so as a comparison, this is what we get. I'm going to show also other implants, what they get, but it's kind of the same story. Each pink line, this is a bit messy, so don't focus too much on that, but I need to clean up this figure. But each pink line is actually a single bank, so one recording that you can do. And you can see that it's very stable over days, and then it tends to decline at a slow pace. And this is when summing, in purple, this is summing over the whole probe. Okay, so that's why we get these large numbers of probes. And this is after selection with automatic curation using bone cell. So this was for one animal. I can also show it for many animals. So here I think, yeah, 31 mice, 19 different probes. Some of the mice actually had 2 probes, just like this purple one actually. And we could record quite stably over the period of, weeks and months sometimes. One big question, and I think it's a pretty unanswered question, is why do we have sometimes like big drops like this? Sometimes it's stable, sometimes actually increasing, sometimes it's dropping. And so to try to understand why on some occasions going up or down, we've tried different things. So maybe it depends on how many times the probe was used. So this is, the probe use is here on the x-axis, and on the y-axis, I'm just quantifying the slope of that. So the more negative and the more like that, it will actually look like. And this is not significantly modulated by the probe use. So it seems that you can reuse the probes as many times as 6 times, and it would be still the same. We've also looked as a function of the position of the implant in the brain on the anterior-posterior position. We don't see a strong effect, but just at the back. And actually, this probe was always inserted in the same region, which was superior colliculus. In that case, this is pretty unstable. And this is something that's been noticed also by other labs, like this very detailed work here, where they try to quantify why things are going down, basically. So this is the average number of units they get per electrode as a function of days. So you see there's a drop at the beginning, and then in their case, it's actually quite stable. And they've tried to break it down as a function of where they were recording in the brain. So the color here, these 2 colors are for the superficial versus deep parts of the brain. You can see in the superficial, it tends to decrease much more than in deep parts. Actually, I think in some parts of the brain, we do see the opposite. And also the AP position. So, at the back of the brain, it tends to decrease more. So this is still ongoing work. It's pretty hard to really pinpoint why some implants are not some implants, but some recordings are better than others. I'm going to go over the freely moving, so I won't show any results actually, but just pictures because I think it's pretty nice to see the size of the implants and so on. So these are the papers that are already published. This is NeuroPixels 1.0. This is the mouse I just showed you before. You can see the size on the head here. It's actually pretty compact compared to what you can have with 1.0. So this is in mice, also in rats from the Brody lab, where you have here 2 probes, but you can put up to 4 probes in that one. And record with that, big corrugated sleeve. Yeah, and with our own implant, we've tried different things. So we've tried NeuroPixels 1.0. This is work by Nat O'Neill and James Reed from the Kuhlman and Lignani labs, where here you can see the implant and the head stage is sticking out, and then it's just connected to the chassis. You have also grounding here. And actually here we don't use any protection because it seems to be working fine. This is another, so this is the surgery I just showed you. This is the end results where you have the probe inside that kind of casing, and then the Spike Gadget's head stage and device here allows you to do wireless recording. And we've also tried dual NeuroPixels 2.0. So I can't remember if this one is dual, but this one definitely is. And in that case, Joanna Catarino, and Jose Teixeira from the Mainen lab designed this head stage holder. In our case, we just use it raw, and it doesn't seem to be too bad for the noise. And we can do freely moving. All right, and now I'm going to go over the challenges quite quickly. The main challenge, it depends a lot on your question, but is the stability. So it may depend on the brain region, and also tracking neurons can be more difficult with reusable implants compared to cemented ones. We'll go over that in the next talk. This is just a summary of the stability of all the different implants. Overall, I would say that it's quite remarkable how stable it is compared when you think about it. We are literally inserting something in the brain and then we can reuse it afterwards. So that's pretty cool. Another challenge is the weight and the size. It's pretty hard to get below 2 grams, and also the height of the NeuroPixels probe make it quite bulky in some occasions. And I know that Emily from the Giacomo lab has designed this pretty tall implant here. It's a NeuroPixels 1.0, and she added these lights to be able to track the mouse, and to avoid it to be too heavy, she uses some pulley systems that I think are also used in other types of recordings. But also one big question is the flexibility. So angles can be difficult, and the number of probes per implant is limited, but also the probe geometry is generally fixed in dual implants. And I know of 2 implants that have been trying to, account for that, where you can independently insert each probe. So this one and this one, where the probes can be inserted at different angles. In our case, so the position of the probes compared to each other is fixed, but you can adjust for a few things by changing the docking module. So you can have it long if you're penetrating only, not so deep in the brain, versus very short if you're going for the depth. You can make the probes further from each other, and you can also have a slanted docking module to allow for an angle. And the final one is the robustness. In big species, this may necessitate some shielding around it. So as a conclusion, I would just say that this is an expanding field. So keep an eye on the news. The implant choice may depend on your needs and questions. And finally, the remaining challenges I've just hinted at: so stability, implant size, flexibility, and robustness. And with that, I would like to thank everyone from the Cortex lab. I won't go through all the names, but basically these are the people with whom I've designed and tested the implants, but also all the different labs, so the Kuhlman and Lignani labs, the Churchill lab, the Vickenheiser lab, Mainen lab, and Rochefort lab, who have been testing the implants and troubleshooting a lot. And also to thank the whole Chronic Neuropixels community. So yeah, thank you. I think that's all.